So today we'll start lecture 40, and here I'm going to make some comments on constraint optimization about how you can improve constraint optimization and some of the topics which are there in this subject which are not really about methods but how you actually pose the optimization problem in terms of the objective function, design variables and so on. And again, I'm Dr. Ranjan Ganguly. Now, one of the things which plagues optimization is the enormous computer time which is frequently required to solve realistic problems. So the cost of calculating the cost function or objective function as well as the constraints can be high in many cases. Now, if you are trying to calculate the gradients of the cost function and the constraints, then this cost is further magnified. Now, one of the things you can do is that you can look at your problem carefully and see if there are some constraints which are not critical. That is, they are actually quite well satisfied or deeply satisfied at your current design points. And therefore, you may actually remove these constraints from your optimization problem when you first solve this optimization problem. So I'll give you an example of a typical design problem such as a wing design problem. Now, typically the goal of any kind of design related to a flight vehicle would involve weight minimization, and therefore some optimization may be performed to minimize the weight of the system while constraints are placed on stress and frequency, for example. So the stress constraints ensure that your structure does not fail. The frequency constraints may ensure that you do not have certain vibration phenomena known as resonance, which can cause structural failure. Now, there is one more problem which happens in flight vehicles, and that is that of flutter, which can happen at certain flight speeds when there is a problem which can cause the whole system to break up and has devastating consequences. Now, the flutter constraint is actually computationally very expensive. So one of the things you could do is that you could perform the optimization problem for weight minimization with stress and frequency constraints, and you can leave out the flutter constraint for now. Now, when you get to the particular optimal point for this truncated constraint set, check if the flutter constraint is actually violated at this point. And in many cases, you may find that actually the flutter constraint is not violated. So in that case, you have saved an enormous amount of computation time by not including flutter as a constraint. Now, of course, there is the possibility that the flutter constraint is violated. For example, if your design is little toward the cutting edge, it's somewhat low in terms of damping and so on. Now, in that case, mathematically speaking, you can use the optimal point which you obtained while you did not consider flutter as a constraint as a new starting design x0 to solve a problem where you have now put flutter as a constraint. So essentially you redo the optimization problem, you add flutter as a constraint, and instead of starting with the first design which you had, you start with the converged design from the case with the truncated constraint set. Now, of course, this particular point is likely to be an infeasible design because flutter was violated there. And so you have to use some methods such as the penalty type of methods which navigate through the infeasible region. You cannot use a barrier method, for example. But once you do that, you will again reach a good point, a solution point, and this is going to be at the boundary where flutter is an active constraint. So this is a general concept which you can use in many cases, and it depends on the particular problem you are doing, your domain knowledge of the problem, and so on. Now, a general thought could be that there is always a problem about getting good starting designs. And one of the ways to get a good starting design is sometime to look at a very reduced constraint set, get a solution for that particular problem or even for the unconstrained optimization problem, and take one of the solutions which you have obtained. You don't have to take X star, but take one of the XKs which are those which satisfy the constraints, for example, as a starting design. So you could actually run an unconstrained optimization problem for some time. You could look at the various xk values you have obtained. You look at the fact that whether these xk points satisfy the constraints and so on. And then you use this point as a starting design which may have just started to get into the infeasible region. Now typically if you have posed the optimization problem quite well, your optimum is going to lie on the constraint boundary. And this is because generally most design problems would require constraints to get a feasible solution. For example, if I am designing a structure such as a beam, if I have no constraint, then essentially the mathematics would tell me that the breadth, height, length of the beam should be 0. Basically, there should be no beam. But there are some constraints which essentially force the mathematics to choose a physically viable solution. Now, sometimes you can also create this using move limits for the problem. So that is recommended if you are doing an unconstrained optimization problem for an actual physical system. You must include move limits to prevent completely useless solutions from being thrown back at you. It's also important to spend some time studying the different constraints which you have put in the optimization problem, see how useful and how important they are and whether they are going to become active at the optimal point. Now, one of the ways of figuring out what are the important constraints and design variables for the problem is to use your knowledge of problem physics or the domain you are dealing with. So if you are working on a mechanics problem, you better know mechanics quite well or find somebody who knows mechanics quite well. Now, one more way to handle this, and this becomes important because many times you use optimization on a problem for which you may not have much familiarity in terms of past physics. So if you are designing a UAV system or something like that, then this may be the case. So in those cases, you can do parametric studies, or there is a whole field called sensitivity derivative calculations. And these particular parametric studies and sensitivity derivatives will tell you something about which design variables are most important. Now in parametric studies, you essentially vary the value of the different design variables and see how the cost function and the constraints behave when you vary these values. So you could fix one value or a few values and you could move some of the values. So basically parametric study lets you get a picture of the system from various dimensions. And the sensitivity methods which are there are very important sensitivity methods such as the Sobol method and so on, also let you get a good picture about which are the key design variables for the problem, and this can help you severely truncate the set of design variables. Now there are some methods proposed by researchers such as Papalambros and Wilde, which essentially talk about model boundedness. So again, these can be used to investigate the constraints and design variables and the cost function itself. In certain problems, the number of design variables can be reduced by using the symmetry of the structure or some other physical property. So for example, if you are designing a composite layup or you are designing a building, maybe all the floors of the building are going to be exactly same. So some of these aspects can be used to significantly reduce the number of design variables. Now, one more thing to keep in mind is that in manufacturing or in real life situations, it is preferred to have a system which is simpler and more uniform. So for example, you could be using an optimization method and you could get a very non-uniform variation of certain physical properties such as flexural stiffness and mass of a beam. But then you may find that it is actually less desirable and very difficult to manufacture this beam, and it would have been better to have a simple linear or quadratic variation for this particular problem. So sometime you will see people using very complicated functional representations of design variables, and these may actually not be particularly useful, because in contrast to what happens in mathematics where all kind of functions are possible, in actual physical systems it is generally preferable to have lower degree polynomial type of functions or exponential functions or something like that to represent any kind of thing which can actually be given a physical manifestation. Though with 3D printing a lot of things have become possible, but still for practical purposes you would require more reasonable manifestations of the real system. Now there is also the concept known as reduced basis, which can be used to reduce the number of design variables. Now this concept uses the fact that there are many systems which have actually been produced by experienced designers. These are good but suboptimal design. For example, if we take the kind of sections which are used in a typical wing, then there are many of them which have been proposed for the last many decades. And so instead of developing a completely new section, we could combine some of these designs and develop a new section. For example, let us say there is a combination of many designs. So there are Y1, Y2, Y3 to YM or M designs. A new design could be represented as a composite function of these prior designs. So you could use I is 1 to M, some coefficients here, each of these designs here, and then some constant vector here. And now this is a typical wing section. Now many wing sections have been proposed, so I could take Y1 to YM as being the main wing sections which have been proposed for a certain flight regime, such as laminar flow, and then I could essentially create a new wing section based on this kind of method. So now what has happened, instead of taking all these different coordinates around the wing section here, I only have to consider these AI as design variables, which are much smaller in number. So this is essentially the reduced basis for this problem. So I have reduced this whole problem from keeping all these coordinates around the wing section to simply calculating a number of AI. And my design is essentially a combination of all these particular designs. And in many cases, such a design may come out to be quite well, because it is using the information from a lot of the past designs and it is slightly changing them to obtain a much better design. So this particular method was proposed by van der Plaats in the context of airfoil design. Now, as I mentioned, each design vector may have thousands of design variables, which are the coordinates of this particular section. And then you could use this method, or you could use a general optimization method to develop the airfoil section. You could use a fluid mechanics code, something like Xfoiler, and then do the optimization. And that is certainly possible in many cases, especially if you have high level of computing power. But let's say you are constrained in terms of computing power, then you can use the reduced basis also to come up with a pretty good wing section for your particular problem. So these sets AI are known as the reduced basis. Now, one more important technique in optimization would be to not actually use the objective function and constraints, but use some kind of Taylor series approximation. Now we have seen some of that concept in the sequential linear programming problem, in the quadratic programming problem, and so on. Now, if you could extend these things or these concepts, you could take any particular function coming out of a computer code. You could create Taylor series expansions. Typically quadratic expansions would be quite good, and then you could replace the actual functions or computer programs with these particular functional representations which you have obtained. Now, of course, remember that Taylor series is going to give you polynomial approximations. So, of course, polynomial approximations are pretty good and they are quite valid in the neighborhood of the current point you are in the design space. And typically, most search methods move around the current point in the design space. So, these kind of possible approximations of the cost function and constraints are going to be very good somewhere around the point xk where you are currently at. So you start with x0, get the approximate solution around it, find the particular optimal point, then move to x1, once again repeat that process and keep moving forward. Now, of course, here you would need to put some kind of move limits or checks around the current point so that you do not go too far away from the current point xk, because in that case the approximations you have made will degenerate. Now, typically, finite difference approximation is used to calculate these derivatives, as you can imagine, because most of these derivatives are coming from computer programs. And then these finite difference derivatives are used to construct these Taylor series of the constraints and the cost function. Now, one of the tricks here is that since your finite difference derivatives are expensive, you may not want to update your approximation at every k value. So maybe you can change these approximation every now and then, depending on some norm or measure you have created. So essentially, then you can take rough values here. You can also use rough derivatives. And then the constraint optimization problem is solved as a sequence of these approximate problems. So these methods have been there for quite some time and have been used to get many solutions for problem, for example, in rotorcraft design optimization by Chelly and several other researchers. Now, as you start thinking about these kind of concepts, you will realize that you may be able to build good approximations of the objective and constraints by using change in the design vector and change in these functions. So this is something to consider. Also, instead of taking very small perturbations in the Taylor series, which is typical, you could take relatively larger perturbations about the baseline point and create your Taylor series functional approximation. So this concept was actually played around a lot with Taylor series, and then finally it gelled into the response surface method, where some people realized that you can use a different approach. Instead of using the Taylor series to create these functions, you could use theories based on the design of experiments, which is a field which is somewhat disparate from our current field. But in fact, that's where they decide where to run their experiments at a set of points so that they can form a good model of the system. And essentially, this concept can be extended to the computer part of the equation, where you have a computer model and you need to run this computer model at several points so that you can get a good approximation for the system. So again, once this was discovered, various researchers such as Hafka and many of his co-workers, and then it spread around to different people, the response surface method became a very powerful approach, because people realized that you can essentially decouple the analysis problem and the optimization problem, and therefore you can create some kind of functional representations of the computer code and then use the plethora of methods which are out there to solve these much simpler problems. Because if you are dealing with simple functions which are polynomials or similar to polynomials, then it is much easier to use the plethora of optimization methods which have been developed by various people. And in fact, today you have these kind of methods coded up in various higher level programming languages such as MATLAB, and therefore you are capable of solving many important problems by using the response surface method. So that's a method which we are going to consider in the next chapter of the book, and then we are going to go into detail about that particular method and how it has resulted in a kind of revolution in the optimization field. It's also sometimes known as surrogate modeling, because essentially you are replacing the actual mathematical model of the system by a surrogate model, or sometimes also known as a meta model, which is a model of a model. So I will close this video here. This ends lecture 40, and I will see you in my next video.